What's this strange glow emanating from this tube? In 1920, 25 years after he discovered X-rays and their application in radiography, Konrad Röntgen, on the brink of retirement, continues to wonder about their true nature. He remembers all those weeks spent in his laboratory, working night and day with the kind of equipment that makes us smile today: a camera, fluorescent products, some homemade cathode ray tubes. Memories of before the war, always intact. A Ruhmkorff coil to produce the electrical current necessary to his experiments. Further on, a hand-operated vacuum pump and some small test tubes. Witness of his discovery, the X-ray of his wife's hand. And then, in 1901, the first Nobel Prize for Physics. Very quickly, industry discovers the utility of his discovery, and medicine even more so. The First World War would bring X-rays into general use. Indeed, they made it possible to locate the bullet and shrapnel that were the source of so many infected wounds, saving tens of thousands of lives. Transported in ambulances, a rudimentary installation makes it possible to take X-rays close to the fighting. In the early equipment, a combination of electricity and joinery do a pretty good job, producing very effective X-rays. Unfortunately, there was no protection for the patient and the doctor against their harmful effects. These first radiographs were often of good quality. A metal projectile is quite visible in a patient's wrist. But how did this extraordinary discovery come about? To find out, let's go back in time and find Professor Röntgen in his laboratory on November 8, 1895. Röntgen contemplates with curiosity a fogged photographic plate that his laboratory assistant had just developed in error. On the photograph, the silhouette of a small cardboard box containing a metal part. These objects were placed in the drawer of his office. Röntgen is extremely intrigued. So, while he was testing a cathode ray tube the previous day, mysterious rays crossed the office and exposed the photographic plate. This was the start of a long process in which reflection and intuition would lead to a dramatic discovery. Initially, he observes the flutter of fluorescent substances located at some distance from the tube when operating. Obviously, radiation is escaping from the tube. A fluorescent screen will be useful for him to control his tests. Interposed between the apparatus and the screen, a large book lets these mysterious rays pass through. Is this new radiation identical to cathodic radiation? Röntgen remembers an old experiment. A winch is placed in a cathode ray tube and starts moving when a voltage difference is applied to the electrodes. According to the polarity, the winch winds forward or back. Cathodic radiation is known as corpuscular. That is, it's present in the form of a kind of wind of particles. Another experiment to remember, that of Professor Lenard. He'd observed that having passed through a fine aluminium membrane, placed at the exit of a cathode ray tube, the rays disappeared after traveling a few centimeters through air. Röntgen is now convinced these rays he's investigating, and which pass through matter without disappearing, can't be cathode rays. He surrounds the tube with a perfectly opaque black fabric to see whether they're ultraviolet rays. A metal object packed carefully in a cardboard envelope is placed between the tube and a fluorescent screen. After switching on the tube, the object is quite visible on the screen. The rays passed through the fabric. But even stranger, these rays are stopped by the bones of a hand. Röntgen patiently builds a small metal spiral staircase. After a long exposure, and by examining the photographic plate, he notes that the absorption of these X-rays increases with the thickness of the metal. The radiography of the object illustrates this result perfectly. Something else to note. The experiment was formerly carried out in a tube fitted with a Maltese cross. As the experiment shows, the cathode rays are deviated by the magnetic field of a magnet. This reveals that they are electrically charged. Röntgen thinks of something else. According to the laws of electromagnetism, speed, v, the magnetic field, B, and the electromagnetic force, F, are laid out along 3 directions, perpendicular to each other. The direction of vector F, the force, is determined by the polarity of the particle. He concludes from this law that the particles circulating in a cathode ray tube are negative. Does the new ray have the same properties? Moving his magnet in all the directions between the tube and the screen, Röntgen notes that the image of the metal key remains motionless. On the other hand, the action of the magnet on the cathode rays inside the tube causes them to deviate. On the screen, the trace of the X radiation moves with the movement of the magnet. Röntgen concluded that X-rays are therefore produced at the level of the wall of the tube, at the point of impact of the cathode rays. X radiation is thus different from cathodic radiation. The image of his pen holder seen through a prism provides him with the idea for a new experiment. He sends a very narrow luminous ray through a prism. In blue, the incidental luminous ray. The prism will partially refract it, in red, and will reflect it in yellow. It should be remembered that at that time, physicists knew only visible light, infrared, ultraviolet, and more recently, radio waves. Now he interposes his prism between the tube and the screen. Contrary to visible light, surrounded on the image, X-rays revealed by the fluorescent screen do not undergo any deviation. A magnifying glass does not influence them either. Röntgen concludes the laws of geometrical optics do not apply to X-rays. One avenue remains to be explored. Is X radiation actually a wave? The undulatory nature of the light is easily highlighted by a device presenting 2 narrow slits at a close distance. Through a magnifying glass, we see the monochromatic light producing figures of diffraction and interference. The photography of the slits shows interference rings, alternatively brilliant and obscure. Röntgen installs the same device, but by using a cathode ray tube as a radiation source. After a long exposure, the radiography does not reveal any interference. Only the clear image of the 2 slits appears. X-rays are therefore different from light waves. If the X radiation passes through matter, even dense matter, this could perhaps be useful in industry. Complex metal objects, such as his rifle, could be analyzed without disassembling them. This process will give rise to industrial radiology. By radiographing his hand, Röntgen also understands the importance of his discovery for medicine. For the first time, the autopsy of the living being is possible thanks to medical radiology. After 6 weeks of intensive work, on December 28, 1895, Röntgen publishes a complete description of the properties of X-rays. During a public meeting, he presents his experiment to all the professors at the University of Würzburg, on January 23, 1896. Only in the 20th century we will understand how these rays are really produced. In an X-ray tube, a cathode emits electron projectiles which are violently attracted by the anode. The collisions which result from it cause the appearance of X-rays. Let's explain this. At the level of the atoms of the anode, the electrons, in blue, revolve in various orbits around the core, in red. Let's briefly immobilize the outer shell electrons in order to have a better understanding of how X-rays are produced. If an electron projectile has suddenly passed close to the core of the atom, it undergoes a modification of trajectory and is heavily braked. The energy lost by this braking effect reappears in the form of small wavelength X radiation, which means it's very penetrating radiation. On the other hand, if an electron projectile circulates further from the core, it will be decelerated less, and it will produce X radiation with a longer wavelength. Consequently, it will be less penetrating. If, finally, the electron projectile collides directly with an orbital electron, there'll be an electronic readjustment. Energies of these X-rays emitted in chain obviously depend on the electronic structure of material. But even today, matter has still not yielded up all its secrets. In his table, Mendeleev had reduced the elements composing matter to a mere 100. This was in 1870. 60 years later, it's thought that everything can be explained by 3 particles: protons, neutrons, and electrons. Matter seems to have revealed all its secrets, but not for long. 30 years later, more than 200 new particles were discovered. Everything became complicated again. In the 80s, the evolution of knowledge brings back this complex world to 3 families of particles. Science evolves in successive stages, going from the complicated to the simple. In 1870, 100 elements. In 1930, 3. In 1960, 200. In 1980, 30. Many questions remain unanswered. Why do these particles have such different masses? What law controls this apparent diversity? Behind appearance, reality hides. Scientists think there's still a long way to go before that reality is finally revealed. The exploration of the universe is only just beginning.